Hello, my dear students. Welcome to Power Electronics GATE and ESC classes, continuation of Power Electronics concepts. In this session, I would like to discuss about types of power semiconductor devices. Students, all of you concentrate. We know that there is a different types of semiconductor devices are there. Here I am giving different classifications. First, I am giving the general classification. In general, the devices are switches. Here I am telling that devices are switches, students, because every device is used as a switch. Here I am explaining the devices means indirectly I am explaining the switch concept. I told already in power electronics, whatever the semiconductor devices are there, all the devices are used as a switches. I am explaining devices means indirectly we are studying the types of switches also. First we will see the general classification. In general, the switches are classified into one is ideal switch and another one is practical switch. Now I have to discuss what exactly ideal switch and what are the properties of ideal switch and what exactly practical switch and what are the properties of practical switch. We know that in general the switch can be represented like this. This is the representation of switch, friends. Here this is one representation of the switch. The switch can be represented like this, or we can also represent the switch like this. But here I am explaining ideal switch. Ideal in the sense practically this type of switches are not possible. One operation of switch is nothing but a one on and one off. That means a switch operated in the saturation region and cutoff region. Saturation region means on switch. Cutoff region means off switch. That is, first we will see what exactly ideal switch. Why it is called ideal switch, friends. Ideal switch is a switch that does not consume or dissipate any power from its source. It cannot dissipate or it cannot consume any power from source, then it is nothing but a ideal switch, friends. But point to remember, the switch can be represented like this or the switch can be represented like this. If the switch is on state, what is the observations? If the switch is off state, what is the observation? That I have to discuss. But point you have to remember, friends, one operation of switch is nothing but a one operation of switch is nothing but a one on state and off state. That is on state and off state, students. In on state, what are the observations? In off state, what are the observation? That I have to discuss. Here I am discussing the ideal switch, students. Once again I am repeating, I am discussing the ideal switch. Ideal switch. Practically this type of switches are not possible. Now we'll see, if the switch is on, what are the observations? Operation of switch. If switch is on, if switch is on, switch is on means switch is closed. Switch on means switch is closed. That is switch closed, students. Very important observations you can expect for any competitive point of view. Based on these types of devices or switches, already the questions are framed GATE, ES and PSU's point of view also. That's why whatever the observations that I am giving, that you have to concentrate. Switch is closed. If the switch is closed, what is the voltage across the switch, friends? Ideally, I am telling that. Ideally, if the switch is closed, the voltage across the switch equal to 0. VSW equal to voltage across the switch. And it carrying the current. It carrying the current. I am talking about voltage across the switch. I am not talking about supply. I am talking about the voltage across the switch and current through the switch. Clear, friends? Point to remember here. I am explaining the with respect to switch or device. I am explaining the switch means indirectly I am explaining the devices. Here I am explaining ideal switch means indirectly I am explaining the ideal devices. Okay. Then voltage across the switch. But voltage across the switch is 0. If the switch is closed, voltage across the switch is 0. But what about the current? It carries any current. Sir, why I am telling that any current? Because it is ideal. That is, it carries any current from minus infinity to plus infinity. It carries any current from minus infinity to plus infinity. But point to remember, students, if any switch is conducting, if any losses takes place in a switch, those losses are called conduction losses. Mainly in switch, there is the three types of losses exist. One is conduction losses, blocking losses, another one is switching losses. If the switch is conducting, if any losses are takes place, those losses are called conduction losses. If the switch is off state, if any losses are takes place in a switch, those losses are called blocking losses. If the switch is switching from on state to off state and off state to on state, if any losses are takes place, those losses are called switching losses. Now, this is ideal switch. During conduction, voltage 0, but current is exist. Because of voltage 0, then what is the power loss? Sir, what is the power loss? Power loss is nothing but a product of voltage into current. Na? But in ideal switch, what is the voltage if the switch is closed? 0. If the voltage is 0, then what is the power loss? 0. What power losses? Conduction losses, because switch is on state. Na? That is, in ideal switch, the conduction losses equal to 0. In ideal switch, the conduction losses equal to 0. Okay, these are the observations from ideal switch. That is, if ideal switch is on state, if the ideal switch is on state, what are the observations? Voltage across the switch equal to 0 and it carries the any current from minus infinity to plus infinity. Then what about the conduction losses? The conduction losses are 0. But one operation of switch is nothing but one on and one off. Na? Next, you see if the switch is off state. If the switch is off, switch off state means switch is open. Switch off. Switch off means switch open. Switch open, students. But I told already, switch is on state means the switch is operating in which region? Switch on means the switch is operating in which region? That is operating in saturation region. That is operating in saturation region. Switch open means that is operating in which region? That is operating in cutoff region. That is operating in cutoff region. Yeah. Switch open. Okay, this is the equivalent. If the switch is open, what are the observations, friends? Switch is open. Is there any current through the switch? That is the current through the switch equal to 0. Ideally. But practically, take any device. During the operation, if the switch is open, take the example diode or BJT. If it is under off state, there is some leakage current up to some time. But here I am talking about ideal. Na? That's why the current is 0. But it blocks any voltage from minus infinity to plus infinity. I am not talking about supply. I am talking about the voltage across the switch. Because of ideal, it blocks any voltage from minus infinity to plus infinity. That is, if the switch is open, the current through the switch equal to 0, students. And what about the voltage? It blocks any voltage from minus infinity to plus infinity. Current exists, but current 0, but voltage is exist. Current 0, but voltage is exist. What is the power loss? 0. If both current and voltage is exist, then only power losses are takes place. But here current is 0, only voltage is exist. That's why power loss is 0. Then what type of power loss this? Switch is off state. Na? Those losses are called blocking losses. That's why if the switch is off state, the blocking losses equal to 0 in ideal switch. Blocking losses equal to 0. Yes, friends, the conduction losses are 0. Then what about the blocking losses? The blocking losses also 0. Conduction losses are 0. The blocking losses also 0. But there is one more type of losses are takes place in a switch. Those losses are nothing but a switching losses. But it is ideal switch. In ideal switch, the switching losses also 0. In ideal switch, the switching losses also 0. The switching losses also 0 in an ideal switch. Sir, why? Why the switching losses are 0 in ideal switch? Because there is instantaneous switching from on state to off state and off state to on state. See, here the switch is conducting, here the switch is on state, and here switch is off state. Switch is conducting means it carries the current. Switch off state means it blocks the voltage. But see the observation here, students. What is the observation that you have to concentrate? From on state to off state, suddenly current is falling, and suddenly voltage is rising. Suddenly current is falling, suddenly voltage is rising from on state to off state. If it is moving from off state to on state, if it is moving from off state to on state, I am talking about transition. On state to off state transition, off state to on state transition. If it is moving from off state to on state, voltage is falling, current is rising. Again, current is falling, voltage is rising. Again, voltage is falling, current is rising. But there is no time between on to off and off to on transition. Then on time equal to 0, off time equal to 0. Once the on time and off time is 0, there is no any switching losses. But practically, every device is having its own turn on time and turn off time now. But here ideal switch, there is no any on time and off time. Then what is the reason for switching losses equal to 0, students? There is no, that is, there is instantaneous switching, that you have to write. There is a instantaneous switching, instantaneous switching from on state to off state and off state to on state. Switching from on state to off transition and off state to on transition. Okay, that's the reason why switching losses are 0. Now, what are the total power loss, friends? We know that the total power loss equal to that is PL equal to conduction losses plus blocking losses plus switching losses. These are the switching losses, I am denoting as a SL, and these are the blocking losses. These are the blocking losses, I am denoted as a BL, and these are the conduction losses, I am denoting as a CL. Then what is the total power loss? The total power loss in ideal switch equal to 0. If the total power loss is 0, students, what is the temperature rise? What is the temperature rise? Power is dissipated in the form of heat now. If there is no power loss, what is the temperature rise? The temperature rise equal to 0. If the temperature rise is 0, then what is the cooling requirement? No need of any cooling requirement. That is, no need of cooling requirement. Like heat sinks or any water cooling or air cooling, that requirements is not required in the case of ideals. But practically this is not possible. This is only ideal case. That is no need of cooling requirement. No need of cooling requirement. Okay, these are the observations from ideal switch, students. Now, based on these observations, I have to draw the characteristics of an ideal switch. That we will see. How to draw the characteristics of an ideal switch. But here I am giving one generalized statement, students. Throughout, wherever you are drawing the characteristics of a devices, this point you remember. In drawing of characteristics of a devices, currents are taken on y-axis, voltage is taken on x-axis. That is fixed. Unless otherwise specified, always you have to take the current on y-axis, voltage on x-axis for drawing of characteristics of a device, VI characteristics of a device. I am not talking about quadrant operation of the power electronic circuits. I am talking about characteristics of devices. In drawing of characteristics of devices, the current is taken on y-axis. Let this is ISW, this is minus ISW, and voltage taken on x-axis, students. This is VSW and this is minus VSW. Then how to draw the ideal characteristics? We know that if switch is on, what is the observation? If switch on, students. If switch on, what is the observation? If the switch is on, voltage across the switch is 0 and it carries any current from minus infinity to plus infinity. Correct or not? Minus infinity. Now, these characteristics I am representing here. These characteristics here I am representing, students, that you have to concentrate. That is voltage 0, it carries any current from minus infinity to plus infinity. It carries any current from minus infinity to plus infinity. Then if the switch is off state, what is the observation, students? If the switch is under off state, What the current through the switch? The current through the switch is 0. It blocks any voltage from minus infinity to plus infinity. It blocks any voltage from minus infinity to plus infinity. Then that characteristics also I am representing here. It blocks any voltage from minus infinity to plus infinity. It blocks any voltage from minus infinity to plus infinity. Like this, we can draw the ideal characteristics of a switch or device. I am discussing the switches means indirectly I am discussing the device. I am discussing the devices means indirectly I am discussing the switches, because every device is used as a switch. Okay, this about what is the observations from ideal switch. Clear? Next, you have to see what exactly a practical switch and what are the observations from practical switch. A practical switch has non-zero resistance in on state and finite resistance in the off state. That is, if the switch is conducting, it must offer some minimum resistance. If the switch is blocking, it offers some resistance. In the case of practical switch, there is no instantaneous switching from on state to off state and off state to on state. That is, if it is moving from on state to, if it is transition from off state to on state or on state to off state, there must be some minimum time. There is no instantaneous switching. Okay. Because of this reason, in any practical switch, friends, the conduction losses are not equal to 0. Why conduction losses are not equal to 0? Because of forward voltage drop. Because of forward voltage drop. See, for example, let us assume that if the diode is conducting, students, ideally I am telling that conduction losses are 0. Take the practical case. If the diode is conducting, there is some voltage drop across the diode. No? There is some forward voltage drop or not? Because of that forward voltage drop and forward current, there exists some loss. That's why that is nothing but a conduction losses because of forward voltage drop. Due to forward voltage drop, there exists a conduction losses. That's the reason why conduction losses are not equal to 0. In a practical switches, blocking losses are not equal to 0. Sir, why blocking losses are not equal to 0? Take the example again, diode. If the diode is under off state, means reverse bias condition. Under reverse bias condition, there is some leakage current through the diode. No? Yes or no? There is some leakage current through the diode. That leakage current into voltage. The diode is blocking the voltage. Na? That voltage into leakage current gives some power loss. But in ideally, there is no leakage current. That's why blocking losses are 0. But practically, there is a leakage current and some voltage across the diode. The voltage, no doubt at all, under off state, the diode is blocking the voltage. But up to some, there exists some leakage current. What is the leakage current? All this we will see in the diode operation. Yes. Then because of leakage current, what about the blocking losses, students? Not equal to 0. Then there exist switching losses also. That's why switching losses not equal to 0. Why the switching losses are not equal to 0? There is no instantaneous switching from on state to off state and off state to on state. I will show in the characteristics in the next slide. Wait for that. That is, there is no instantaneous switching. There is no instantaneous switching. Concentrate. There is no instantaneous switching from on state to off state, from on state to off state, on state to off state, and off state to on state, and off state to on state. Yes, friends. Then conduction losses not equal to 0, blocking losses not equal to 0, switching losses are not equal to 0. Then what is the total power loss, students? Power loss equal to conduction losses plus blocking losses plus switching losses not equal to 0. Then total power loss is not equal to 0. Total power loss is not equal to 0. If the total power loss is not equal to 0, then what is the temperature rise? Temperature rise is also not equal to 0. This is very important observation. During the operation of any device or switch, if the power loss is not equal to 0, there must be some temperature rise. If there is a temperature rise, that switch or device must to be operate within safe operating area or safe operating region. That means within the thermal limits. This statement I am not given for ideal switch. Why? There is no any temperature rise. But during the operation of any semiconductor device or switch, students, if there is a temperature rise, it must to be operate within its thermal limits, within its safe operating area or safe operating region. If you operate beyond the thermal limit, due to high temperature rise, the device is permanently damaged. But point to remember, every device is having its own safe operating area or safe operating region. BZT is having its own safe operating area. MOSFET is having its own safe operating area. SCR is having its own safe operating area. IGBT is having its own safe operating area. Based on the safe operating region or safe operating area, 1 or 2 times the questions are framed in ESC exam. Okay, that what is that characteristics also I will give. You please go through that characteristics of safe operating area of different devices. We can expect for other PS. Even for GATE exam also we can expect. Still now not framed, but we can expect, students. Okay. Then temperature rise is not equal to 0. That is practically, if the temperature rise is not equal to 0, practically in any device, if temperature rise not equal to 0, if temperature rise not equal to 0, it must be operating, yes friends, operating safe operating area or safe operating region. Safe operating area or safe, that is thermal limit. Otherwise, the device permanently damaged. Permanently damaged means you don't repair again. Temperature rise will causes the permanent damage. The device permanently damaged. Permanently damaged. Okay. Now see what is the safe operating area of different devices. First I will give the general safe operating area. Next I will give what the safe operating area of the different devices. Before that, you see the practical characteristics of a devices. These are the practical characteristics of a general switch. The general switch practical characteristics I am giving. What is the observation here, students, that you will see? Here, switching transition. This is on state transition. On state transition means current is rising. That is current through the, I am not talking about supply. I am talking about the current through the switch and voltage across the switch. The current through the switch is rising. Voltage across the switch is falling. This transition is called on state transition. That is, what is the observation during on state transition? During on state transition, very important, students. On state transition, what is the observation? Current through the switch is rising. Current through device is rising. Current through switch or device is increasing. And voltage across the switch is falling. I am not talking about supply. Supply is whatever you given, that is constant. But I am talking about with respect to device or switch. Voltage across switch is falling. Correct? Switch is falling. This is the one. Current is rising now. Voltage is falling. This is on state transition. On state transition. This is turn on transition or on state transition. T on is nothing but turn on time. This is during turn on transition means during T on. But here once completely turn on, it is conducting. It is conducting. Once it is conducting means it is carrying the current. This is the conduction mode. Conduction mode. If the device is conducting, practically there is some voltage drop across the device, students. If the device is conducting, there is some on-state voltage drop. This is the on-state voltage drop. This on-state voltage drop into current gives conduction losses. This is what is the meaning of conduction losses. This drop into current gives the conduction losses. But this gives the turn-on switching losses. This region, which losses takes place? In this region, In this region, which losses are takes place? In this region, turn on switching losses are takes place. Turn on switching losses are takes place. How to calculate this? Later on I will explain. Turn on switching losses are takes. In this region, which losses are takes place? This current into this voltage drop gives the conduction mode. In that conduction mode gives the conduction losses. Next, here current is falling. Concentrate, here the current is falling, students. Current is falling. If the current is falling, what is the voltage across the device? Voltage across the device is rising. Current is falling, voltage is rising. Then this is called turn off transition. Then what is the observation during turn off transition? What is the observation during turn off transition? During turn off transition, current through the device is falling. That is, current through switch is falling. Current through the switch is falling. What about the voltage across the switch? Voltage across the switch is rising. Very important observation. Based on this observation, already question is there in ESC exam. What do you mean by turn on transition? What do you mean by turn off transition? That is very important, that you have to concentrate. Then during this turn off transition, which losses are takes place? Turn off switching losses are exist. Turn off switching losses. Concentrate. Turn off switching losses are exist. Turn off switching losses are exist. Clear? Then again, what is this state, students? What this state? The current, now that the device is completely turn off. The device is completely turn off. There is some leakage current. There is some leakage current. Now it is blocking. The voltage is blocking. Then this is which mode? Blocking mode. During this region, which losses are takes place? Blocking losses are takes place. That is what do you mean by blocking losses? Voltage blocking into leakage current. This is the observation. What the switching losses, what the conduction losses, what the blocking losses in a practical switch. But in a switching losses, there is a turn on switching losses and turn off switching losses. Conduction losses are during conduction. Blocking losses are during blocking mode. Take the example, diode reverse bias, blocking. Diode conducting, conduction losses. Diode from on state, that is off state to on state, turn on switching losses. Off state to on, that is on state, off state to on state is turn on switching losses. On state to off state is turn off switching losses. The total is nothing but a switching losses. Okay, these are the observations. Now you see the what is the safe operating area or safe operating region. Okay, this statement I already given, students. If any switch, if temperature rise not equal to 0, that means during the operation in any switch, if the temperature rise is not equal to 0, it must be operated in safe operating area or safe operating region. Otherwise, due to high temperature rise, the device may be permanently damaged. Then this is the one of the safe operating area. This is a general safe operating area representation. In general, the safe operating area can be represented like this. Simply you can remember like this. Here, this is the safe operating area representation. I am representing the safe operating area like this. This is called safe operating area or safe operating region. Here I taken the current and here I taken the voltage. But you have the doubt here, sir. Why we have to represent safe operating area is like this? Why not like this? Why not the safe operating? The safe operating area cannot be represented like this. The reason is, I am giving one example that you have to concentrate. See, for example, take the example of 500 volts, 50 ampere diode. If you take this example. Sir, what is the meaning of 500 volts, 50 ampere diode? If the voltage across the diode is 500 volts, if the voltage across the diode is 500 volts, the current through the diode is 150 amperes. This is not the meaning. This is wrong. If you assume like that, if the voltage across the diode is 500 volts, I am not talking about supply. I am talking about the across the device and current through the device. If the voltage across the diode is 500 volts, if the current through at that time current is 50 ampere, what are the power loss are? 500 into 50, 25 kilowatts. The device is permanently damaged. That is meaningless. Then what is the meaning of 500 volts? If the diode is under reverse bias condition, okay, this is the meaning. What do you mean by 500 volts 50 ampere diode means? If the diode is under reverse bias condition, it blocks the voltage of 500 volts. At that time, current is not 50 amperes. At that time, current is very small leakage current. Very small leakage current. Clear? If the diode is under forward bias condition, it carries the current of 50 amperes. It carries the current of 50 ampere. At that time, the voltage drop is very small voltage drop. The voltage drop is very small voltage drop. Corresponding to this voltage, the current is very small. Then you can join this. Then what the safe operating area, students? We can get the safe operating area is like this. That's why always the safe operating area is represented like this. We never represent like this. This curve indicates average power dissipation curve. Average power dissipation curve. That means if the device is blocking high voltage, current is very small. If the device is carrying high current, the voltage across the device is very small. That is the meaning. If the voltage is high, current is less. If the current is high, voltage across the device is less. Voltage across the device, that is nothing but a safe operating area. We never represent safe operating area like this. That's the reason why there is a curve like this. Now in this, what are the different regions it indicates? That is also very important. This region indicates the thermal limit, and this region indicates the secondary breakdown, and this region indicates the voltage limit, students. But every device is having its own safe operating area or safe operating region. Now we'll see that safe operating area of the different devices. Maximum up to now in GATE exam, based on this, no question, but already 1 or 2 times it is framed in ESC exam, that you have to concentrate, students. Here I am giving the safe operating area of the BJT in forward bias safe operating area. In forward bias safe operating area, in y-axis I taken the current, in x-axis I taken the voltage. If you take like this is forward bias safe operating area of the BJT. That is a forward bias. Safe operating area of the BJT. Safe operating area of the BJT. Forward bias safe operating area of the BJT. Okay. Now what this region indicates? This is asking in competitive exam. What are the different regions it is indicates? For example, let us assume that this is A, this is B, and this is the C, and let this is the D, let this is the O. What is AB region indicates? Device dissipation limit, power dissipation limits. This is secondary breakdown limit. This is the device operating voltage limit. And what this OA indicates? This is the current limit. Like this, the questions are asking, students. Okay, that you have to consider. This is the forward bias safe operating area of the BJT, that is bipolar junction transistor. Next, this is also safe operating area of the BJT. This is a reverse bias safe operating area of the BJT. Reverse bias safe operating area of the BJT. Safe operating area of the BJT. In reverse bias condition, then what this limit indicates? The peak current limit, and this indicates the temperature limit or device power dissipation limit. This one. Okay, these regions it is asking, students, that you have to concentrate. Okay, and this what this limit indicates? Peak voltage limit. This indicates the peak voltage limit. Okay, this is in reverse bias safe operating area of the BJT. Like this. Then what is the safe operating area of the MOSFET? Metal oxide semiconductor field effect transistor. MOSFET stands for metal oxide semiconductor field effect transistor. Then this is the safe operating area of the MOSFET, where AD is the maximum limit for DC. This AD indicates maximum limit for DC. Maximum limit for the DC. DE is the maximum rated temperature. DE is corresponding to DE is the corresponding to maximum rated temperature, where DE is the corresponding to maximum rated temperature, students. Maximum rated temperature, that you have to concentrate. What is the EC? EC is the maximum voltage capability for VDSM for MOSFET. That is this EC. This is the EC indicates this limit. This EC is there now. This limit EC indicates maximum voltage capability VDSM for MOSFET. Then what is OB? OB indicates this OB. This OB. This is O and this is P. This OB indicates, okay, that you have to concentrate, and this OB indicates, friends, that is a maximum drain current. VDSM means drain to source maximum voltage. VDSM means drain to source maximum voltage. Okay, these are the limits it is asking, that you have to concentrate. But one observation here, friends, this 1 milliseconds, 0.1 milliseconds, 0.01 is nothing but a pulse width. Pulse width in the sense on time. Pulse width in the sense on time. If pulse width is decreasing, this is for 1 milliseconds, this is the safe operating area. For 1 millisecond, this is the safe operating area. This much of region is covered. For 0.1 milliseconds, friends, for 0.1 milliseconds, this much of area is covered. This is the safe operating area. This is safe operating area for 0.1 milliseconds. What about for 1 millisecond? This is the safe operating area. Up to this region only it is operating, below this. 0.01 milliseconds, what the safe operating area? This much of region is covered. Below this it is covered. That means if the pulse width, that is on time, if pulse width is reducing, what the safe operating area? The safe operating area is increasing. That means if the device is on for less time, then we are covering the more safe operating area. If the device is on for more time, we are covering the less safe operating area. Okay, this observation is important from safe operating area of the MOSFET. What is VDSM? Drain to source maximum voltage. Drain, what is the drain voltage? What is the source voltage? What is the gate voltage? All these that you will see in the MOSFET, you already studied even in analog electronics also. But in power electronics point of some statements only I will explain with respect to MOSFET and BJT. That is, for MOSFET, there is no distinction between forward bias safe operating area and the reverse bias safe operating area. That means this is applicable for the safe operating area for both forward bias safe operating area and reverse bias safe operating area, students. For both the cases, it is applicable for MOSFET. For MOSFET, it is applicable for both forward bias safe operating area and reverse bias safe operating area. And one more observation, if pulse width is decreases from 1 milliseconds to 0.01 millisecond, the safe operating area is increased. Just now I told already this statement. Clear? Okay, this observation that you have to concentrate. Next, this is the safe operating area of the IGBT. What is IGBT? In detail later on I will discuss. Insulated gate bipolar transistor. Insulated gate bipolar transistor. Insulated gate bipolar transistors. That is IGBT. Then this is the IGBT safe operating area. This is the safe operating area of the IGBT. That is the forward bias safe operating area. Forward bias safe operating area of the IGBT. Safe operating area of the IGBT. IGBT, that is the insulated gate bipolar transistor. Okay, this you see the same observation here. This, if the time is pulse width is decreases, pulse 10 power minus 5 seconds, 10 power minus 6, that is here also if pulse width is decreases, the safe operating area is increases. The safe operating area is increases. That you have to concentrate. Okay, this is the different safe operating areas for different times. Below this region, next below this region, that you have to concentrate. This VC is the collector to emitter voltage. This is the maximum or peak current of the collector current. Peak current of the this indicate the current limit, peak current limit, students. Let this is O. This is O point. Then OB indicate the peak current limit. Next. Then this is the safe operating area of the IGBT in reverse bias condition. That is safe operating area of IGBT in reverse bias condition. In reverse bias condition. Reverse bias condition. Okay. Now what is the observation here? If the safe operating area is increasing, if the safe operating area is increases, then what is the dV by dt limit is decreasing. That is, more the safe operating area, lesser will be the dV by dt limit of the device. Okay, that observation that I given, you please go through this. OA equal to ICM, that is the maximum collector current for DC and voltages up to AB equal to VCE. This is the maximum collector limit up to AB equal to OC. That is AB equal to, that is here I given AB equal to VCE. This is AB equal to VCE. Okay, this you have to take the, this is the VCE voltage, and you have to take the notation is AB equal to VCE. This point you take, this is A, this AB equal to VCE. Okay, okay, that you have to take observation is, no need to take this, have to take like this. VCE is the corresponding to VCE voltage, students. Corresponding to VCE voltage, the maximum collector current limit is the collector limit equal to ICM. That point you have to concentrate. Corresponding to VCE. If pulse width is decreases, what the safe operating area increases, that you know. If reapplied voltage increases, the reverse bias safe operating area is decreases to avoid the latch up. What is the latch up in the device, in latching of the SCR, that I will explain. But up to you remember, if the safe operating area is, that is, if this voltage is increasing, higher the voltage, lesser will be the safe operating area to avoid the latch up in the device. That is, if reapplied voltages is increases, the reverse bias safe operating area is decreases. If pulse width decreases, then safe operating area is increases. Reapplied dV by dt increases, reverse blocking mode safe operating decreases to avoid the latch up. Higher the voltage, lesser will be the safe operating area. Are you observing or not? This one, see, this is the higher the dV by dt, na? Higher the dV by dt, na? If higher will be the dV by dt, the safe operating area is below this one only. Below this one only. This is the safe operating area. If this is low value, if dV by dt is low value, if the dV by dt is low value, and this is the safe operating area, then below this one, this total is the safe operating area. Don't take only this portion, sir. This total is the safe operating area. Clear? That's why higher will be the dV by dt, lesser will be the safe operating area. Low, if dV by dt is less, more the safe operating area. This total is the safe operating area. This total is the safe operating area. Yeah, these are the observations from the safe operating area of the practical devices. Yes, friends, with this, what exactly ideal switch? What is the observations from ideal switch? And what is the practical switch? What is the observations from practical switch? And what is the safe operating area of the ideal switch? Sorry, what is the safe operating area of the practical switch? No need of any safe operating area for ideal switch because there is no any temperature rise. Yeah. A safe operating area for practical switch. What is the safe operating area of the BJT, MOSFET, IGBT? All this I explained. Okay, this is one classification. The next classification is very important, that I have to discuss what are the different types of devices in power electronics. In power electronics, there is so many devices are there. There is a first classification, second classification, third classification, fourth classification, fifth classification, like that. So many devices are there. From that also we can expect the question, student, that you will see. Okay, this is about what exactly ideal switch and practical switch. I am explaining ideal switch and practical switch means indirectly I explain ideal device and practical devices.